All right, so we're going to introduce these two methods, Jacobi iteration and the Gauss-Seidel method, both at the same time here. Let's start out by just looking at the equation that we're solving. We have the equation ax equals b, and so I've just written that out here, same thing you've seen all before, and I just wrote it out for a 3x3 system because we could write it out for more, but that would just take a lot longer, and you get the same thing in the end. So you should be able to understand it with just this, but you could write it out for more. That'll be for you to do on your own. That's great. In all your spare time. Okay, so we have this equation. So all I've done is what you can do. So this is really similar to the concept of fixed point iteration that we looked at to find the roots of an equation. We looked at fixed point iteration. We also looked at how we could use fixed point iteration to solve a nonlinear system of equations. So this should look very, very similar to that. So what we do is we just solve each of these equations for x. So we have this equation because we write all these out, and so we have one equation. So we solve that for the first equation for x1. So x1 equals b1 minus a12 x2 minus a13 x3 all over a11. So that's x1. We solve for x2 in the second equation, and we solve for x3 in the third equation. So we've solved for the x's here. Now the problem is that we don't have any x's, right? If we knew x2 and x3, yeah, sure, we could compute x1, but since we don't know x2 and x3, then how are we supposed to compute x1? And we're going to do it the same way that we always do it with an iterative method, is we start out with a guess or with something that may be hopefully close. In root finding, we like to try to start with something close, but regardless, so it's just going to be a guess, and so as an initial guess, you can just guess x2 equals 0 and x3 equals 0, and you put that into the first equation, and so you just slip them in, and so I'm going to show them both here, and so you just slip 0 in. For x2 and x3, you solve the first equation and you're going to get an estimate for x1, okay? And you can do the same thing for this equation x2. You could put zeros in for x1 and x3, and actually, so this starts to get at where the differences are between Gauss elimination and the Gauss-Seidel method and Jacobi iteration. But see, that's the idea. So you just get your x1s, x2s, x3s. So you start out with 0, but then as you get guesses, you just start plugging them in, and you keep doing this over and over again. Go x1 through x3, x1 through x3, x1 through x3, and you keep doing this until hopefully you get closer and closer and closer to the solution. And just as before, you can have a method that your iteration may converge or it may diverge. So you can have the same problems that we had with the open methods used for root finding. So let's look then at the differences here. Okay, what the differences are is in the Gauss-Seidel. So I've written them out, and at this point they're the same because I haven't highlighted the differences yet. We have x1 equals, so we just plug in our initial guess for x2 and our initial guess for x3 to compute x1. Okay, so that's what we do in Gauss-Seidel, and then we compute x2 equals b2 minus a2 x1. Oh, okay, so we have x1 here. So then the question is, do we use our initial guess? So initially maybe we said 0 for this and 0 for this, and so but we've computed an x1 here. So do we use 0 or do we use the x1 that we just computed? And for Gauss-Seidel method, we go ahead and use the x1 that we had previously computed, and then the x3, well, we're going to have to put in a 0 because we don't have one. All right. So the same way then for the next equation. Okay, so then we have an approximation to x2, and then we have to decide, okay, well, what are we going to do down here? And so in this one, we actually do use this x2. We go ahead and use that x2 there, and we also use the most recent x1 as well. We also use the most recent x1 in this equation as well. Alright, so we're always using the most recent, the latest and greatest in the Gauss-Seidel method. Jacobi iteration is a little bit different. For Jacobi iteration, if we're going to start out with initial guesses of 0, we just go ahead and we put them in everywhere in all three of these equations. And so with Gauss-Seidel, you've got to solve the first one before you can solve the second one. You've got to solve the second one and the first one before you can solve the third one. That's not true with Jacobi iteration. See, we do x1, x2, x3. We just do them all in one batch. So I've got an initial guess for x1, an initial guess for x2, and an initial guess for x3. And I just go through and all in one batch, I come up with my new x1, x2, x3. Then I take these x1, x2, x3s, and I use them in the next set of equations. So x1, see, I'm just going to use that x1 here, or well, the x2 there, and the x3 there. So I'm going to use those guesses in my when I compute x2. I'm going to use the x1 from there, and I'm going to use the x3 from up here. Similarly, again, the x1 from the previous step, and the x2 as well. That's not what we do for the Gauss-Seidel method. For the Gauss-Seidel method, again, we're always using the latest and greatest guesses. So we have x1, and then we have this x3. Well, we're just going to take this x3 from the previous, and we're going to use it. We're going to use this x3 down in this equation. Then we're also going to use, so we had x2, so we had this x2 that we computed here. We're going to use this x2 down in this equation. Okay, so then we keep moving. Our next equation, so we're going to have x1, so this x1 gets used right there. The x3, again, we use the latest x3, so we're going to be using that x3 in here. Also, next equation, same thing, x2, so we got to take this x2, and we got to plug it in here. Okay, and also, of course, use the latest x1. And it sort of becomes a spaghetti mess here, but you see what's going on. That's the Gauss-Seidel method, where the Jacobi iteration is a little bit, oh, I'm trying to close my picture. The Jacobi iteration is a little bit simpler because you can do them all in one batch. But typically, if you're going to choose between the two, you'll typically stick with the Gauss-Seidel method. And the reason you'll typically stick with the Gauss-Seidel method is because it tends to converge faster, because we're always using the latest guesses. Where with Jacobi iteration, we're not using the latest guesses all the time, and so sometimes it doesn't always converge as fast, and so we'll do different things. So that's your introduction to the Gauss-Seidel method and Jacobi iteration, except as with any iterative method, there's one more thing that we need to talk about, and that is the stopping criteria, right? When do you stop? How do you know that you're close enough? Because it's not like before where we just finish the algorithm, we've got the answer, and we're done. And so the answer to that question is the same way as we did before. You remember we had this stopping criteria. Well, we do the same thing. In this method, we define some epsilon. So epsilon we define some epsilon s, and if epsilon a, so we stop when epsilon a is less than or equal to epsilon s, right? And so well, the absolute value really is all we care about, and epsilon a is defined as we just take, and it's not just epsilon a, it's going to be for a specific I. We're going to have an epsilon a for x1 and for x2 and for x3, and so that's going to be absolute value of xij minus xij minus 1 over, and this is all absolute value, over xij. No, I shouldn't write it like that. ij. So same notion as before, and this is times 100 to get a percent. Same notion as before. We are using the old minus the new, or the new minus the old, doesn't matter, because it's the absolute value. Old minus the new, or new minus the old over the new. Okay, so that's how we get our percent error, and that's how we determine when to stop when we've met the stopping criteria for all I.